Welcome to the Math Record. Today we'll be covering inverse derivatives. This video will cover part 5 of chapter 2 of our calculus class. Okay, let's begin. In part 3 of chapter 2, we briefly covered the concept of inverse derivatives using trigonometric functions. In this video, we'll be covering inverse derivatives more in general. Okay, let's remind ourselves how inverse works. So if we have a function, we could denote this as f of x. Sorry about that. Draw a little bit more clear. F of x. Then our inverse could be denoted as f to the power of -1, which usually is just stand for inverse of x. So the inverse of f. So as you know, whatever's the input for f of x is going to be the output for the output for inverse f of x. So if x is all the values you could put into f of x, and y is all the x are all the inputs of f of x, y is the output for f of x when you plug in x, right? Then basically inverse would be the y, and this one would be the x. So the inputs are the y's, and the outputs are the x. So whatever you have for your input is basically your output for this one. So if you have a coordinate for f of x is like 2, 3, right? Then the inverse function will have a coordinate 3, 2. Okay, that's the general idea of how inverse works. So we're going to use this idea to get our derivatives. So if we have this, technically we could always just write the equation f inverse, which is inside it, is equal to x, right? Because let's say you have the 2 points, right? 2, 3, and 3, 2, right? So this is our f, and this is our inverse of f. So if we plug in 2, right, if we plug in 3 into x here, that means we get 2, right? And since f of 2 is equal to 3, and we plug 3 in initially, they're basically the same thing. So whatever you plug into x, into inverse of f, and then you put the normal function f on it, it would just be the same, whatever you put in, your output is just the same as your input. So this definition is true. And we also have the same thing if you kind of just switch which one's inside and which one's outside. So you have the inverse of f of x, right? So this one's true also. So you have 2, 3, and you have 3, 2, right? So if we plug in 2 in here, f of x will equal 3, right? So that will be f of the inverse of f of 3 is equal to 2. So you just plug in 2 and you got 2 back out. So it's the same thing. So whatever you plug for x input for f, and then you take the inverse of that, you basically get your input again. So it's like getting an equation, doing that equation on it, and then you reverse the equation so you get back the original input. That's basically what you're doing. And that's the basic idea of inverse functions. So now we just need to find the inverse of these. So let's just start with the first one. Okay, we'll deal with the other one later. This will be our first way to find inverse derivatives. So this could just be a chain rule, right, for derivatives, because you just have an equation inside another equation. So as you remember for chain rules for derivatives, you work from outside in. So your outside is f of x, right? Because if you kind of ignore the inverse f, we just have f of x. So so you work for the derivatives for the first outside equation. So it's just f. So the derivative of f, and then you keep whatever's inside the same. So you have f of -1 of x. And then you just multiply that equation, this entire equation, right? The derivative of f, if you plug in the inverse of x inside that x, you multiply that by the second chain. So our second chain is basically the inverse of whatever's still inside. And whatever's still inside is just the inverse of f. So that would just be f of the inverse of f and the derivative of that. Basically the derivative of the inverse of f. So that was only for the left side. So now the right side, we just need to do the derivative of that. So the derivative of x is 1. This is the same idea that I used for for our trig video in 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 a video that we covered previously in chapter 2. So if you want to see how we use that for inverse trig using normal trig functions, then you could check out that video. But this video will cover inverse functions more in general, and how to find inverse derivatives without even finding the graph of inverse. Okay, so this is our first method that we're generally gonna use, and then there's the other one. Okay, and now we have this function. So this is our second function. Our first function was the f, right? This function was our first function had f outside, and then we have f inverse of f inside, right? Now we have f inside and the inverse of f outside. So how would this work? So first, it's the chain rule again, right? You have f inside of the inverse of f. So technically, you just had to chain. So the first equation, the first equation is inverse of f. So we had to, so that's our first derivative. So f inverse of f, and then whatever you keep inside, you just keep inside. So f of x, right? And then we had to find the derivative of this. So, right? I'm putting on these commas just so then, brackets so you understand. So I could use a different color so you understand why I use these brackets. Okay, we have white. Let's just keep the white out here for once. -1. And then let's switch this to red. Just so we could keep track of where the brackets are. It's not anything significant, but I just want you to not misunderstand what I'm doing. Okay. That's red. And then we have our next white. And then we have the derivative of this, right? So you plug in f of x into the inverse of f, and then you find that derivative. So that's your first chain. It just follows the basic chain rules. I'm putting these in different colors so you don't mess up which parentheses is covering which equation. And that was our first chain. So our second chain is whatever's still inside. Our derivative inside is just f of x. So we just have the derivative of f. F. And then that's for our left side. Our right side is just x. So derivative of x is just 1, right? A derivative of a linear is always just constant. If there's like something in front of that constant, like 2x, right, then the derivative is just 2, right? But since the constant is just 1, then you just put 1. Basically just that simple. And we're going to use these methods to find out an example for how it works. How inverse derivative works. So let's kind of try that example. Okay. So let's use our first equation. We'll use f, right? The first one we use. The first derivative, which is the derivative of f of inverse, right? So then you multiply by the inverse derivative. And derivative and 1, right? So this was our first equation, which is the first method we could use, because it just depends on which equation you want outside. If you want your original equation outside and your inverse inside that, and you take the derivative of that, this will be your output. And now we just need to find the values that we need to look for. Okay, so first we want to find out what we want to find the derivative of. We want to find the derivative of the input, right? Of the inverse, right? So this is the thing we need to look for, because this is the inverse derivative, right? So f to the power of -1, which is inverse, and then there's that apostrophe, which is just the derivative. So this is the one we need to look for. Let's try an example. Let's have f of x equal to x to the power of 3 minus 2x squared. Sorry about that. That looks like a 3. Then minus x, and then plus 4, okay? And we want to find the inverse derivative at x is equal to 2 or something. Okay? So let's try this, right? So you want to find the derivative at x equals to 2. So we could just plug in 2 here, and then we basically get the inverse derivative, right? So we just need to find this part of the graph, this part, and then we could just divide this number, 1 divided by that number, and we get the inverse derivative, right? So now we just need to focus on this part, on this portion of the equation. Okay, so we need to find the inverse of, right? So if we have f1 and you plug in that 2 for x for this portion, what is this, right? So you gotta remember what inverse and that f of x and the inverse of f works, right? So the input for an f is the output for an inverse of x, right? And the output for f is the input for inverse of x. So when we have the inverse of x a 2, this 2 means it's the output for, because the 2 is the input for inverse of f. So technically the output is just 2 for f. It might seem confusing, but whatever you have for your input is going to be your output. And whatever is your output is going to be your input, okay? So that's just a general idea how to think about it. You don't have to confuse yourself too much. If you get an input, just make it into your y. So you think your input is your x, right? Change it to a y. If you think you have an output, which is your y, change it to an x. Basically, it's just that simple. So you have 2 is equal to your equation, right? Because we want your original equation. The only equation you have left is this. So you just use this equation. So as I said before, for inputs and outputs and how they work. So we have 2x to the 3 minus 2x squared, and then minus x plus 4, right? So we minus 2, so that's x squared, that's 0, is equal to x cubed minus 2x squared minus x plus 2. So let's kind of somehow factor this out, right? So I noticed I could put these together. So we could have the negative x and x to the power 3, and we could have the negative 2x to the power 2 and plus 2. So we could factor this out by grouping. Usually it's not that simple, but I'm just using a really easy case for here. So we have x, so we could just factor out the x. So factor x out of x to the power cube is x squared. Factor x out of x minus x is negative 1, right? And then you have this thing, negative 2x to the power 2 and 2. So we could factor out negative 2, right? So you factor out negative 2 from here, you have x to the power 2. And you factor out negative 2 from positive 2, which is x minus 1. See right here, we have x squared minus 1, x squared minus 1. So it's the same terms. So you have x. So technically, this could be written the same thing as x minus 2 and x squared minus 1, right? You can still factor out x squared minus 1, which is just x plus 1 times x minus 1. Right? So it's just really that simple. It's just a simple like pre-calculus polynomial grouping and like separations to factor. It's for calculus, you could probably use your calculator for this to find like the x's if you want. Doesn't matter. The point is that you need to find out when the x's are. So the x's, you have one at 2, you have one at negative 1, and you have one at 1, right? So that's all you need. So those are your values, 2, negative 1, and 1. Okay. So when we take the inverse of 2, that will be equal to 2, negative 1, and 1, right? Because that's what we got. So we plug this in here. So we have inverse of 2 when x is equal to 2. Then you could just say f of the inverse of, the derivative of f for 2, because we have 3 answers, 2, negative 1, and 1. So we have 3 possible answers. So we have f of 2, and then we have derivative of f at f equals negative 1, at derivative of f at negative 1, and derivative at 1. Right? So now we just need to find the derivative of f of x. So the derivative is just bring down the power and then subtract 1 from the power. So you have x to the power 3, so that's just 3x. And then 3 minus 1 is 2, so you have 3x squared. Okay? Next one, 2 times 2 is 4, so minus 4x. 2 minus 1 is 1, so you have 4x to the power 1. This is power to 1, x is just a linear is just a power to 1, so then bring the 1 down, So -1 times 1 is just -1. I'm not going to write the 1. And then 1, right? The exponent 1 minus 1 is 0. So technically, that's x to the power 0 is just 1. So you just have this. So, and a derivative of a constant is always 0. So your derivative of f of x is equal to 3x squared minus 4x minus 1. So it's basically just that simple. Okay, I'll delete this for a bit so then we could get a little bit more room. So we have the derivative of f of x is equal to 3x squared minus 4x minus 1. Okay, now we just need to plug in these values so we can find the derivative at 2, derivative at -1, and the derivative at 1. So let's start with 2. Plug in 2 here, that's 4, that's 12. That's 4 times 2 is 8, so that's -8, and that's -1. So that's -9, and that's 3, okay? So this one is equal to 3. Next one, let's do -1. Plug in -1 here, so that's 3. -1 to the power 2 is just 1, so that's just 3. -4 times -1 is 4, so it's just plus 4, and then you minus 1. So that's 7 minus 1 is 6. So this one is just equal to 6. Now you plug in 1. So 3 times 1 to the power 2 is just 3. -4 times 1 is just -4. And then you minus 1. So that's -1 and then -2. So this one is equal to -2. Right? So now we just got this entire left side. Right? Because if you because initially we got x is equal to 2, so we found the inverse of inverse of f, and then find x inverse of f at 2, which is equal to 2, -1, and 1. And then we just find the derivative at 2, -1, and 1, and we got 3, 6, and -2. Right? So now we have, let's just delete this equation, because we don't need this for now. We don't need this right now. Okay. So we have these three numbers, 3, 6, and 2. So when you have this, right, you plug in x is equal to 2, you have inverse of f derivative. Sorry, let's actually put the 2 in here. And then you're multiplying by a number, which we have 3 different numbers because we had 3 different answers for the inverse output, which is 3, 6, and 2, right? So we have 3, 6, and 2 multiplied by whatever. There's 3 separate equations, but I'm too lazy to write it. Sorry about that. Which is equal to 1. So we want to find the inverse derivative at 2. We just divide by that number. So it's just 1 divided by 3, which is 1/3. 1 divided by 6, which is 1/6. Sorry, that looks bad. 1/3. 1 divided by 6 is 1/6. And 1 divided by, sorry, that was -2. And 1 divided by -2 is just -1/2. Right? So the inverse derivative of at 2 of f of x would just be 1/3, 1/6, and -1/2. So usually your equation will look like this, right? Not exactly. I'm just drawing a rough shape because our f of x is cubic, right? Because x to the power 3. Then our inverse derivative would look something like this, right? Because it's kind of just rotated in respect to y is equal to x. Okay, so it kind of looks something like this. So whatever you have, just kind of rotate it like 90 degrees. It kind of just looks like that usually. And then we have this, right? So if we want to find at x is equal to 2, we have like x right at these points, right? So there's a point here, there's a point here, and there's a point here. That's why we have 3 solutions. So we have a slope. This one's probably the -1/2. And either this one is the 1/3 or this one's the 1/3, and one of them is 1/6. You can find out which one by just having these points, right? So you have x is we have it at 2, we have 1 and -1. So we have something at like 2 here, right? And this is 1 and this is -1. So -1/2 is -1, right? It's the 6. So when we have the 6, we have 1/6. So at -1 is probably 1/6 right here. And that's how you could basically just guess it using the numbers. And that's basically the first way to do it. We have 2 equations, remember? This is the first way. when we had when we had, let me delete this because we kind of solved the example. So this was the first way when we have f of f of -1. F inverse of f is equal to x, and we found the derivative of this, right? We found the derivative of this entire thing. Now we're gonna try to find f of -1 of f of x is equal to x, and we want to find the derivative of this. So what happens when we use this case? It's basically a different method, but gets the same answer. I'm doing both ways so you understand which one you could do. So you could, so whatever way you like to do it, you could just change vice versa. But you like the first way better or the second way better, it's just personal preference. Okay, so our second equation is f of the inverse of f of x, right? And then we took the derivative of that times the derivative of f, right? Which is equal to 1. So we want to find the derivative of the inverse. So where is the derivative of the inverse? It's right here. It looks ugly, like because there is a f of x inside, but we could kind of just think about it and then we will solve it that way. Usually this way is the not preferred way because there is an equation inside while the other equation had a derivative of f, like just by itself, which is faster. But this way is also viable if you want. So let's try the same equation. So we have f of x equals to x to the power 3 minus 2x to the power 2 minus, minus x, and then plus 4. And we want to find the derivative of x equals 2, right? It's the same example. We're just going to show it with method 2. Okay? So we need to find the derivative of inverse of f at 2, right? So we want to find this, right? So when we look at this, we just want this and this to be the same. So we have 2 is equal to f of x, right? So that's all we need to do. So getting that general idea, we have 2 is equal to f of x. F of x is x to the power 3 minus 2x to the power 2 minus x plus 4. Doesn't this look similar to what we just did last time? Yeah, it's basically it. It's basically the same process. But now we're just looking at it through a different way. So minus 2 is x to the power, sorry about that, x to the power 3 minus 2x squared minus x plus 2, right? So factor by grouping again. It's basically the same thing I just did last time. So it's just x squared minus 1, right? Because x cubed and minus x. And then minus 2. So divide 2 by negative 2x to the power 2 is just x squared. Divide negative 2 by 2 is negative 1, right? So it's the same thing. So you have x minus 2, x squared minus 1, that's equals 0. And then you can split out x squared minus 1, so you get x minus 2 times x minus 1 times x plus 1, right? So it has the same x's as x is equal to 2, x is equal to 1, and x is equal to negative 1. This is the exact same process we did last time, but now basically we're just looking at through a different equation, as I said before. So we have 2, 1, and negative 1. Okay? So that's what we have. We could delete all this work. If you're doing this on paper, you probably don't want to delete it so you can have like extra credit. I mean, not extra credit. Like you're able to like check your work. So, but I'm deleting it because I'm running out of space. So when we have f of x is equal to 2, right? X will equal to we have x would be equal to negative 1, 1, and 2, right? Because that's what we solved. So when we have that, we have f of negative 1 of, the inverse of f of negative, sorry. Right? We have f of 2, so we have inverse of f2, because that's what we equal to. We just wanted to find x for that one. So we could plug in 2. So this is what we want to find, times Yeah, x is equal to 2, 1, and -1. Sorry about that. So we put 2. So we have x is equal to 2, and then it gets out 2. We put x is equal to 1, that gets out to 2. X is equal to -1, gets out to 2, right? So those are the three possible solutions. Now we just need to put in when f inverse of x is equal to 2, when the inverse of, I mean not the inverse of the derivative of f is equal to, derivative of f of 2, derivative of x at f at 1, and the derivative of f at -1. Okay, so we have these three equations. So we just need to find those values. So do the derivative of f of x. I did that last time. Same process, basically. So drop the exponent down and then subtract 1 from the exponent. So x cubed is just 3x squared. Negative 2x to the power 3 is just negative 4x. Derivative of -1 is just -1. Right? So you plug in 2, that's 4, that's 12. Minus 8 is 4, minus 1 is 3. So this is 3. F derivative at 1 of f is 3 minus 4, which is -1, minus 1 is -2. And the derivative at -1, which is 3 plus 4, which is 7, minus 1 is 6. Okay, so we have three numbers. We have 3, 2, and -6. Right, so we could just delete this. As said before, you probably don't want to delete it so you can check your work, but I'm running out of space, so I'll just delete. So we have 3, 6, and -2, right? I think that was our numbers. 3, 6, and -2. Yes, so, and that was our f derivative of f at 2, 1, and -1. And that will be equal to our 1, right? So now we just find our derivative at inverse of f at 2, which is just 1 divided by 3, which is 1/3. 1 divided by 6 is 1/6. And 1 divided by -1 by -2, which is -1/2. Right? These are the exact same answers as what we got in our first method, which makes sense, right? Because just because you change your method doesn't mean you change your answer. So basically, it does the exact same process, but you're just looking at it through a different way. So generally, both ways work. It doesn't matter which way you like to do. It's just that if you just understand how derivatives work, generally you could just use the idea of how derivatives work and inverse work. You could just use those ideas to find out your inverse derivative without actually having to find the inverse derivative, right? So we never found out what the equation for the inverse derivative is. And we don't have to because we could just use this idea. So you just know how to chain, it'll be fine. So generally, when you want to solve these equations, as I explained in the beginning, which I just gave the formulas and derived it, just all you have to do is just you want to choose which equation is inside the derivative. So you want the inverse inside the original equation, or if you want the original equation inside the inverse, right? This is all you basically have to remember. If you understand your chain rule, you could just chain it then, and then you could just do all the math. Okay, so this is basically all you have to remember. And that basically covers everything for inverse derivatives. Thanks for watching, and I'll see you at the next math record.